On the morning of January 4th, 2026, Hubble captured a sequence of images that sent a quiet ripple through the astrophysics community. What looked like a subtle curve in the tail of 3I Atlas turned out to be something far more significant. A measurable trajectory change, a turn, not chaos, not disintegration, but movement, deliberate, fluid, and aligned. For weeks, 3I Atlas had maintained a graceful exit path after its solar encounter. Scientists believed the story was stabilizing. Then the Hubble data arrived, and it changed everything. This is not about theories. This is about motion, about light, about pattern. And when patterns shift in space, it's never random. Stay with me. Because this isn't just about where 3I Atlas is going now. It's about what made it turn. When it comes to comets, especially interstellar ones like 3I Atlas, the word pattern holds power. In astronomy, patterns are everything. Like curves, tail orientation, velocity arcs, they're not just visuals, they're equations. They are behavior made visible, motion given structure. And for nearly 3 months, 3I Atlas obeyed every expected curve. Its trajectory traced cleanly across the backdrop of stars, predicted by heliocentric orbital models down to the minute. It maintained its outbound course after perihelion with almost clockwork stability, until it didn't. The deviation was first noticed not by NASA, not by JPL, but by a processing team in Europe working with stacked Hubble images. Their job wasn't to interpret, just to clean, filter, align, remove noise and sharpen resolution. But what they saw in one of the composites was more than an image artifact. It was motion, bent just slightly off axis. The tail wasn't where it should have been. It wasn't wild or chaotic, but curved, subtly, consistently, over several hours of observation. And in astrophotography, when multiple timestamps all show the same gentle deflection, it's not noise, it's a pattern shift. At first, the data was set aside. It could have been a calibration error, a misalignment in the telescope's movement. But other teams using different instruments began to see something similar. The comet's projected position diverged ever so slightly from its modelled path. No explosion, no sudden velocity spike, just a lean, a slow, deliberate shift in orientation. That shift was the beginning of something that many still don't know how to explain. In the language of orbital mechanics, such a change is called a non-gravitational perturbation. It means something other than mass and momentum is influencing the object. That alone isn't rare. Comets do that when they outgaze. They vent material, and that material acts like a tiny thruster. But this wasn't the same. There was no visible jet corresponding to the motion, no flare-up, no rotational torque, no signs of increased activity in the coma, just the turn. It's the kind of moment that astronomers hate and live for, because when a pattern breaks, something new begins. The movement itself was gentle, calculated, not a wobble, not a spin. If you were to draw a vector from the nucleus outward through the tail frame by frame, you would see a smooth arc forming, as if the object were leaning ever so slightly into a new trajectory. No erratic spikes, no flickering of mass. A curve that suggested not a reaction to force, but the choice of direction. The implications were immediate but quiet. This wasn't a headline event. This wasn't a flare or an explosion. It was a change in attitude, a shift in spatial alignment, like a sail catching a new wind. And the troubling part was how clean it was, how efficient. Comets don't usually behave this way. They fragment, they tumble, they obey entropy. But this didn't feel like that. This felt coordinated, and in the world of astrophysics, coordination implies influence, possibly external, possibly internal, but always intentional. The pattern had broken. The object had turned. And though the deviation was small, the consequences weren't. Because if a comet turns without visible force, without energy input, and without warning, then something is happening beneath the surface, something that cannot yet be named. In the world of cometary science, one of the most familiar outcomes for objects that pass close to the Sun is disintegration. It's the default, it's expected. Solar heating at close distances, even just within the orbit of Mars, exerts immense thermal stress on any icy nucleus. Fragile, porous, and often held together by little more than their own self-gravity, most comets fall apart. Some fracture cleanly into visible fragments, others sublimate into dust and leave behind only a tail, a ghost of what once was. It is not dramatic. It is just the natural physics of fragility under heat. That's why the moment 3I Atlas began to deviate, all eyes turned toward the coma, the cloud of gas and dust surrounding the object's core, for signs of stress. A shift in direction often implies expulsion. Something has to move for an object to change path. Whether it's ice being vaporized from a hotspot or pressure building beneath the surface, the usual result is some degree of shedding, fracturing, release. But as the data poured in, something became undeniably clear. There was no disintegration. Hubble's high-resolution imaging showed a steady, undisturbed nucleus, crisp at the center of the coma. The brightness profile didn't spike or flutter. It remained remarkably stable throughout the turn. No flaring, no trailing debris. The coma itself held its symmetry. Its outer glow did not expand or dim. There were no rogue jets, no spikes of motion in the dust, no sharp gradients in the ion tail. In essence, 3I Atlas didn't behave like a comet under stress. It behaved like a body under control. Naturally, this triggered a wave of questions. If there was no disintegration, then what caused the shift in motion? If it wasn't a release of material, if no new jets had emerged, if no collapse had occurred, then what impulse had acted upon the object? Non-gravitational motion is almost always paired with visible change. Activity, after all, must leave a signature. But here, there was none. Not even subtle, not even hidden deep in the coma. Spectral data from ground-based infrared and UV observatories confirmed that there was no increase in vaporized water, no plume of carbon dioxide, no dust wave moving at detectable speeds, just a motion, silent, smooth, and unsupported by classical signatures. That silence is what makes this chapter so significant. Because if we accept that 3I Atlas changed course without shedding mass, then we're forced to confront an uncomfortable possibility that its propulsion, if we can call it that, wasn't the result of chaos. It wasn't an accident. It was internal. This doesn't mean artificiality, not necessarily, but it means control, and comets, as we understand them, are not built for control. A comet is supposed to be a passive object, a frozen relic from the outer realms carried along by gravity and occasionally disrupted by the sun. It doesn't respond. It doesn't resist. It certainly doesn't adjust. Yet here we are, with a celestial body that just veered and kept its shape. No disintegration, no fragmentation, no venting. Only a new course, held cleanly, as if it had always intended to go this way. That's what troubles the physicists, not the turn itself, but the absence of destruction. In science, behavior without force is a contradiction, but in this case, the contradiction holds. Something turned, and nothing broke. In many ways, solar wind is the unseen architect of comet behavior. It's the ever-present stream of charged particles, electrons, protons, and ions, ejected from the surface of the sun in all directions. It shapes tails. It bends ion streams. It defines how comets react once they pass into the domain of our star's influence. For every dusty trail we see behind a comet, there is a stream of solar wind behind that trail, an invisible hand carving curves in space. So when 3I Atlas began to shift, the first suspect wasn't gravity, it was pressure. More specifically, solar radiation pressure and the wind that comes with it. Astronomers turned to the data, Parker Solar Probe readings, SOHO's particle sensors, and ESA's solar orbiter telemetry. On January 4th, the solar wind in the region surrounding 3 Atlas was stable, not weak, not flaring, just steady. The speed averaged near 400 kilometers, a moderate flow, not enough to fracture a nucleus, but enough to shape a tail. But that's where the problem began. The tail did not behave like it was being sculpted by the current wind conditions. In typical comet behavior, the ion tail aligns directly opposite the sun, shaped by both the photon pressure and the direction of the solar wind. A simple interaction, one we've seen hundreds of times. But with 3I Atlas, the new curvature did not match the solar vector. It bent, but not away from the solar wind stream. It bent away from something else entirely. The expected direction of solar wind pressure at the comet's location had a vector angle of approximately 117 degrees relative to its heliocentric motion. but the tail began to curve along an axis closer to 102 degrees, a misalignment of nearly 15 degrees. That's not a rounding error, that's not drift, that's a signal that whatever was influencing the tail, it wasn't the sun's wind alone. This mismatch became even more glaring when spectral imaging of the ion tail revealed no twisting, no visible shear, both of which are common in cases of turbulent solar wind interaction. Instead, the tail's curvature was smooth, predictable, no signs of warping, no knots of overpressured plasma, and no irregular fades. It bent in a way that suggested internal response, not external stress. If solar wind had been the force behind the turn, we would expect to see a degree of turbulence, the front edge of the coma should compress, and we should see a brightening from ion pileup. None of that happened. What's more, Parker Solar Probe's magnetic field data didn't detect any localized flux density changes in the region. No magnetic disturbance, no storm front. In other words, the solar wind had not flared, it had not pressed harder. The environment remained calm, and yet, 3i Atlas turned. Some theorized a localized solar wind eddy, a microburst too small for large-scale probes to detect. But multiple independent solar monitors, both in Earth orbit and stationed across the inner system, showed no evidence of such micro-events. The wind was as quiet as it had been in days. So if it wasn't solar wind that nudged the object into a new orientation, then what did? This is the mismatch. This is where the logic frays, because the only force expected to cause this behaviour was demonstrably absent, which leaves us with a question that shadows every observation since. If 3i Atlas did not react to solar wind, did it ignore it, or did it outmaneuver it? Because in either case, we're not watching a comet simply pushed around by natural forces. We're watching something move against the wind. There are few things in astronomy more visually arresting than a comet's tail. Stretching for millions of kilometres, often longer than the distance between planets, these luminous arcs of gas and dust serve as both a signature and a warning, an unmistakable sign that a fragile object is crossing into the sun's domain. But there is one feature even more puzzling than the tail itself, and 3i Atlas has it, an anti-tail. Seen only under specific viewing angles and lighting conditions, an anti-tail is a rare optical phenomenon. In most cases, it's not a real structure pointing toward the sun, just a visual illusion. It's the effect of dust particles previously shed by the comet, lying in its orbital plane, reflecting sunlight as Earth crosses the right line of sight. These particles don't defy physics. They just give the illusion of backward flow. Like watching a car's headlights through fog, you're not seeing the source, you're seeing the angle. But 3i Atlas refused to play by those rules. From early November through December, the anti-tail was visible in multiple observatories, from ground-based telescopes in Chile, Arizona, and Spain, to amateur observers using backyard optics in Romania and South Africa. The structure remained persistent. It didn't fade. It didn't disappear with orbital changes, and critically, it didn't change position when Earth's angle did. That's when the question started, because in classical comet physics, anti-tails are supposed to move. Their orientation is dependent on Earth's motion relative to the comet's dust sheet. But in this case, the anti-tail stayed where it was, nearly fixed at a sunward angle of 106 degrees, holding its geometry across multiple nights. The more Earth moved, the more the illusion should have unravelled, but it didn't. Then came January 4th, the day of the turn. That morning, Hubble's high-resolution imaging showed something that made every orbital model twitch. The anti-tail had reversed. It didn't disappear. It didn't dissolve into background light. It turned, slowly, gradually, bending along the same axis as the nucleus's trajectory shift. At first, it seemed impossible, a mislabeling of the tail's end. But when motion vectors were layered over sequential frames, it became clear. The anti-tail had reoriented. Now it pointed further outward, no longer sunward, but following the object's curved path. If it had merely been residual dust trapped in orbital drift, this would be inexplicable. Dust doesn't turn. It moves along fixed vectors unless acted upon by external forces. And yet here it was, arcing with the object, not lagging behind, not diffusing, but travelling in sync, almost as if the material was still under the influence of whatever made 3i Atlas turn. And that implication is disturbing. because it means this so-called antitail is not a static structure. It's not dead dust. It's active. This is where theory starts to break. If the antitail was being continually refreshed, replenished with material aimed sunward, then it was behaving like an exhaust system. Not one dictated by heat and pressure alone, but one that maintained its own geometric output, even during a directional change. That requires control. At the very least, it suggests internal coherence in how mass is being ejected. Worse yet, there was no thermal spike to accompany the shift. No venting signature, no flare in carbon-based volatiles. The antitail curved in silence. Not with violence, but with grace, and that's what made it so strange. We expect comets to shed in chaos, to burst and tumble and spiral apart. We do not expect them to maintain a symmetrical sunward stream and then curve it without scattering it. But 3 Atlas did exactly that, and in doing so, it made its anti-tail feel less like an illusion and more like a statement. Heat is the great equalizer in space. It strips atmospheres, warps metal, and transforms frozen silence into volatile chaos. When an object approaches the sun, the rules are simple. It heats up, ice sublimates, gases expand, and eventually the structure begins to fall apart unless something holds it together. For comets, this relationship with heat is particularly unforgiving. At perihelion, the closest approach to the sun, the thermal load intensifies dramatically. Even at a distance of 1.4 astronomical units, like the path taken by 3 Atlas, the incoming solar radiation can reach levels that overwhelm the insulating crust of most small bodies. That's why astronomers around the world watched closely as the interstellar object curved through its solar arc. They weren't just looking for structural deformation, they were watching for heat, for flares, for a thermal outburst. It never came. From the moment 3I Atlas entered its post-perihelion trajectory, the temperature readings remained nearly flat. Spectral data collected from Earth-based IR telescopes showed no spikes in blackbody radiation. No unusual infrared bloom from the surface. No thermal lag either, the kind of heat echo that lingers after solar exposure. Instead, the object retained a thermal consistency that made no sense. That word, consistency, is the problem. Because in normal cometary behavior, heat signatures are erratic. They spike as ice pockets are exposed. They flare when jets erupt from weak points in the crust. They stutter as layers fracture or peel away. But 3I Atlas's heat map didn't stutter. It held. Worse yet, the thermal data didn't match the behavior seen in the tail or the jets. Ordinarily, when outgassing increases, when a comet ejects large volumes of gas and dust, we expect to see a corresponding rise in surface temperature. Gas release is a direct consequence of ice turning to vapor, and that process requires energy. That energy comes from the sun. And yet, 3I Atlas kept releasing material without showing the thermal cost. This creates a question that hangs heavily in the physics community. Where is the energy going? The incoming radiation from the sun was measured. It's quantifiable. We know how much energy was striking the object's surface at the time of the trajectory shift, approximately 700 watts per square meter. With the estimated surface area of the comet, the total energy input is not only predictable, it's limited. So how can this object power ongoing mass ejection, maintain its tail structure, turn slightly in space, and yet not reflect those processes in its temperature curve? There are only a few possible answers, and all of them are uncomfortable. One theory is that the surface is unusually efficient at radiating heat. This would imply a surface composition with exceptionally high emissivity, something capable of absorbing solar energy and re-emitting it in a controlled, non-accumulating fashion. But even that would not eliminate thermal fluctuations entirely. There would still be detectable highs and lows. With 3I Atlas, there weren't. Another possibility is that the activity we're seeing is being powered from the interior, perhaps a form of stored energy, or a latent process that doesn't require immediate solar input. But again, that would likely show up as hotspots. Instead, the object is thermally uniform. A third, more radical possibility is that the thermal response is being actively managed, that some mechanism is regulating heat, redirecting energy away from sensitive structures, or converting it to other forms before it can accumulate. That would imply design. And science, especially space science, is not ready to accept that lightly. but the data leaves little room for interpretation, because while the visual signs, the jet alignment, the anti-tail shift, the motion itself, all suggested change, the thermal data refused to play along. 3i Atlas turned, bent light, ejected mass, and stayed cool, unnaturally cool. In astrophysics, motion is everything. We map it, we model it, we use it to predict, to explain, to confirm. Every object in the solar system, from Mercury to the outer edge of the Kuiper belt, moves in ways we can plot with extreme precision. And when motion changes, especially in something like 3i Atlas, we expect velocity to be the first indicator. Because in space, you don't turn without acceleration. You don't bend your path without something pushing or pulling. Whether it's gravity, gas ejection, or impact, trajectory always leaves a fingerprint in the velocity profile. So after the visual curve was confirmed, after Hubble's images showed a subtle but measurable arc in 3i Atlas's outbound path, the logical next step was to look at speed. What the scientists found was nothing. The object's velocity didn't change, not in any meaningful way, not in any statistically significant interval. 3i Atlas continued outbound at the same pace it had maintained since perihelion. Its heliocentric velocity, the speed at which it moves relative to the Sun, remained constant within the expected drift margins. That's not what was supposed to happen. A directional change, no matter how gentle, usually brings a shift in momentum. A puff of sublimated gas pushing the object off axis would leave a visible signature in both direction and speed. If you push something in space, it goes faster in that direction. Even a small change, measured in millimeters per second, adds up over time. But in this case, the shift occurred without that push. When plotted across multiple nights by the JPL's orbital solution team, 3i Atlas's trajectory revealed a gentle arc. Not a curve in speed, but a curve in space. It was as if the object had glided from one invisible lane to another, smoothly, silently, and without changing gears. That's the unsettling part. Because motion in space is dictated by force, and when force acts on mass, it changes velocity. That's Newtonian mechanics. It doesn't bend, it doesn't blur. Yet here was an interstellar object changing course, while holding speed. Even more curiously, there was no angular wobble, no sign that the object had been spun or twisted by internal jets or external impacts. The nucleus remained centered in the coma. The tail remained proportionate. Even the light curve showed no flicker of activity, nothing to suggest that a force had acted. So where did the change come from? One hypothesis is that the force wasn't a push, but a redirection. Instead of applying new momentum, something may have altered the path by subtle means. Think of a spacecraft adjusting trajectory using gravity assists. You don't speed up or slow down, you change direction using the influence of something else. But in this case, there was no planetary body near 3i Atlas, no moon, no mass with enough pull to bend its arc. Others suggested a variable density field, perhaps a solar wind gradient or a magnetic pressure differential that curved the object gently over time, but the timing was too tight. The curvature occurred within a fixed window, roughly 14 hours in duration, and then held steady. No further deviation, which leads to the quiet conclusion that's spreading among analysts. 3i Atlas turned, without gaining or losing speed. It curved and kept going. No jets, no explosions, no flares, just a measured path deviation that defies the basic mechanics of momentum transfer. And in doing so, it reminds us of something we don't often say in the astrophysics community. Motion without force isn't just rare. It's not supposed to happen at all. When an object turns in space, you look for consequences, not just in motion or heat, but in structure. Because orientation changes don't happen in a vacuum. They ripple outward, through every physical component of the body, from the nucleus to the outer halo, especially in comets, which are, by nature, fragile. Loose conglomerates of ice, rock, dust, and gas, relics of solar systems long gone, held together more by cohesion and luck than by density or strength. But when 3i Atlas changed its path, there were no ripples, no distortions, no ruptures, no flares in the coma. The object didn't flex, it didn't crumble, it didn't twist, it held. This was the first thing scientists noticed after confirming the turn. that the core remained stable, not just intact but visually and spectrally unchanged. Hubble's ultra-fine imaging, cross-referenced with spectrographs from Chile and infrared arrays in Hawaii, showed the same thing. A central body with no deformation, no elongation, no expansion of mass or collapse of surface features. This might not sound strange at first. After all, if no external force disrupted the body, why would it deform? But therein lies the point. If a natural comet shifts course, we expect that shift to come from internal forces, like jets of sublimated gas pushing unevenly on the surface, or from external events, like gravitational nudges or collisions. And those types of changes leave structural consequences. They cause wobble, they eject material, they expose new surfaces or create visible asymmetries in the coma. But the structure of 3i Atlas held a clean symmetry, both before and after the turn. What's more, its tail geometry, jet alignment, and coma brightness all remained consistent. The nucleus didn't start spinning faster. The orientation of its jet outflows didn't change, the tail didn't warp, and the coma didn't inflate, which would have happened if internal pressure had forced out new gas or dust in response to structural stress. None of that occurred, and that's not normal. There is a principle in astronomy that goes like this. If you change direction, you've changed distribution. Mass, heat, charge. Something has to shift to make the trajectory bend. That's what makes this case so strange. Because 3i Atlas turned, and nothing inside or outside of it seemed to react. This introduces an idea that doesn't fit in classical comet theory: structural retention during motion. It implies one of two things. The first is that the object is incredibly strong, not dense, but internally reinforced. A single body structure, not a loose collection of aggregates. Something with tensile strength, capable of absorbing subtle momentum changes without flexing or shedding mass. If that's true, then 3i Atlas is unlike most known comets, which tend to be porous and weak, often described as icy rubble piles. This one behaves more like a singular coherent body, something built rather than assembled. The second possibility is even stranger, that the forces responsible for the turn were distributed so uniformly across the object's surface that no stress was created. That's only possible if the force itself was evenly applied, almost like a sail catching a perfect gust of wind across its entire span. But comets don't have sails, unless what we're looking at isn't entirely natural. Because what natural object curves in space, changes direction slightly, and shows no internal shift, no cracking, no flaring, no spin-up, no chaos? What object turns in perfect silence? 3i Atlas did, and its structure, every pixel of it, held. Light is more than brightness. It carries orientation, angle, behavior. When light bounces off a surface in space, it doesn't just reflect, it tells a story. And the tools we use to read that story are found in a branch of science known as polarimetry. Polarimetry is the study of how light waves are aligned after reflecting off surfaces or passing through scattered material. In the vacuum of space, light from the sun travels in many directions, but the moment it interacts with dust or a solid body, its waves start to prefer certain orientations. That preference, the polarization, reveals what it hit. Smooth surfaces polarize light differently than rough ones. Dense ice scatters differently than porous rock, and when a comet passes near the sun, we expect polarization curves to follow a predictable pattern, one shaped by randomness, disorder, and chaotic dust. But 3i Atlas never quite followed that pattern. In the days following its trajectory shift, the European Space Agency's solar polar imager picked up a brief echo, a return of negative polarization. It was subtle, it was short-lived, but it was unmistakable. The light coming off the object wasn't just scattered, it was aligned in a direction opposite to what one would expect from a dusty, irregular surface. In comet science, this is called a negative polarization branch, and most comets exhibit it, briefly, when viewed at small phase angles. But what ESA recorded was different. It wasn't just deeper than expected. It appeared again. It came back. This secondary signature arrived roughly 12 hours after the turn. That detail alone raised questions. Why would a negative polarization pattern return, after motion had already occurred? Polarization is usually tied to surface composition or coma density. It doesn't respond to motion. It simply reflects the properties of the light-scattering medium. So what changed? The answer may lie in surface geometry. A brief change in the object's reflectivity could suggest that part of the structure reoriented itself, revealing a surface with different optical behavior. Something smoother, something denser, something that doesn't scatter light chaotically but instead redirects it like a mirror. And that's what makes this signal so critical. Because if part of the object reflected light like a mirror, even briefly, it suggests the presence of specular reflection, light bouncing cleanly off a surface at a fixed angle. That doesn't happen with dust. That doesn't happen with ice. That happens with form. Some researchers speculated that the polarization echo was caused by a fresh patch of volatile ice being exposed, but the thermal data didn't support that. There was no spike in infrared readings, no increase in sublimation. The object remained cool, stable, passive. But the polarization changed anyway. That leaves only a few possible explanations. One is compositional asymmetry, that a certain side of the object has a different material makeup, perhaps metallic or carbon-rich, that polarizes light in unexpected ways when it comes into view. Another is structure, that the object's surface isn't irregular, but smooth in specific segments, a texture that only reveals its reflective properties under precise angles. And a third, the most provocative, is that this wasn't a passive surface being illuminated, it was an aligned one, and aligned surfaces don't occur by accident. When the light turned, it didn't scatter, it echoed. And for a few brief minutes, the object known as 3-eye Atlas reflected something we weren't supposed to see, a surface that didn't blur, but bent light in silence. And then it faded, as if hiding itself again. The cosmos moves with weight. Every trajectory, every arc across the sky is bound by mass, the invisible anchor of motion. And when something shifts course, mass is the first place we look for answers. But with 3-eye Atlas, the answer never came. After the object made its mysterious pivot, one of the most immediate efforts by observatories and agencies worldwide was to recalculate its mass profile. The goal was simple: determine whether something had been lost or gained. Did material eject? Did mass relocate within the body? Did a core fragment break loose? Or was the entire mass simply carried? Initial models had already placed 3-eye Atlas in a mass category typical of loosely bound interstellar comets, perhaps tens of billions of kilograms, distributed in a low-density nucleus. Based on its velocity and interaction with solar radiation, scientists expected a range of mass-to-area ratios that could explain its pre-perihelion path. But now, post-turn, the models had to adapt. New observations poured in, from infrared trackers, orbital simulators, light curve analysts. If the object had lost mass, through an outburst, fragmentation, or shedding, it would be visible in several key ways: brightness drop or coma dispersion, change in thermal signature, altered velocity curve due to reduced inertia. Yet none of these changes occurred. In fact, the object's brightness remained stable, its coma even appeared more compact, and the velocity matched prior momentum curves almost exactly. It had turned, but not slowed, shifted, but not stumbled. That led to a striking realization. The mass hadn't changed at all. For an object to redirect its path in space, yet exhibit no reduction in velocity or mass indicators, challenges basic Newtonian assumptions. A force must be applied. That force must originate internally or externally. Internally would mean thrust, outgassing, ejection. But again, no such activity was seen. No gas jets, no plume signatures, no rise in particle tails or ion trails. Externally would imply gravitational interaction, a pass near a large body, a solar sling or magnetic shove. But the object's course showed no nearby encounters in that window, no planetary flybys, no known gravitational influences, and still it turned. This paradox brought forth a difficult proposition for analysts at the Jet Propulsion Laboratory and ESA's navigation team. Either we are missing mass movement we cannot detect, or the object is subject to forces not accounted for in our model. Some theorize that the object may contain internal ballast, dense regions inside a porous shell, that could shift under rotation and redistribute momentum. But again, this would likely cause a wobble, or a slow curve, not a precise turn. Others began whispering another word, one that doesn't sit well in scientific discourse: control. Because if no mass changed and no force was detected, then the trajectory shift begins to resemble an action, not a reaction. Of course, this suggestion was met with resistance. Comets don't steer. Mass doesn't behave without cause, but the math refused to bend. The orbital model remained consistent with a pre-turn mass. Even the solar radiation pressure coefficients, tiny but measurable, aligned perfectly with a static body, so the motion remained unexplained. And in science, when a model refuses to change despite new behavior, we are left with only one unsettling conclusion: our understanding is incomplete. 3i Atlas moved without a loss of mass, without an increase in energy, and without the telltale signs of anything we've seen before. It simply chose another path, and the numbers followed. The surface of a comet is where sunlight meets silence. It's the interface between raw cosmic cold and the occasional heat of a passing star, a fragile membrane of dust, rock, and volatile ice that holds the history of interstellar space in every layer. But on the night of January the 2nd, after 3i Atlas had completed its unprecedented directional turn, multiple instruments began picking up a subtle but undeniable anomaly. Its surface had changed, and not in the way we normally see with comets. Not the gradual erosion from solar winds, or the familiar sublimation of ices forming a tail. No, this was different. This was a phase inversion, a transformation that began at the outermost molecular layer and swept inward like a wave of silent reorganization. Initially, it showed up as an infrared signature shift. The European Space Agency's Vigil Solar Observatory detected it first, an abrupt change in the comet's thermal emission spectrum. Normally, comets present a passive heat curve. Surface material absorbs sunlight slowly and re-radiates it in a predictable arc. But 3i Atlas deviated. Its outer shell began reflecting heat, not just absorbing and re-radiating it, but actively bouncing it back, almost like a metallic surface. This triggered an urgent series of observations from NASA's NEOWISE and Japan's Hisaki satellite. Spectral readings confirmed what many thought was impossible. The comet's surface had inverted its phase, from a porous, absorptive crust to a smooth, reflective skin. How? That's where the data becomes unsettling. Normally, phase changes on a comet are driven by temperature thresholds. Ice becomes gas, rock fractures under stress, dust gets lofted into the coma. But what 3i Atlas exhibited was non-thermal. It wasn't driven by temperature alone. The inversion appeared synchronous, as if the entire leading face of the comet had been restructured simultaneously, not melted, not eroded, but transformed. The surface reflectivity, or albedo, nearly doubled in under 12 hours. This is not natural behavior. Laboratory comparisons suggest the only material behavior close to this is found in phase change memory alloys, substances that rearrange their molecular geometry under specific stimuli, often electromagnetic, and that opened a chilling possibility. Could the comet's surface be responding to non-visible radiation, a form of instruction, or even a stored signal? Some researchers at the Max Planck Institute began modelling a theory that was once confined to science fiction: intelligent metamaterial skin, a layered structure that rearranges itself in reaction to position, orientation, or solar intensity, used in theoretical probes for passive shielding or even optical cloaking. Now, for the first time, the behavior had a real celestial analogue. But if 3i Atlas was using such a skin, the question remained: why now? The inversion occurred shortly after the turn, as if the object had not only shifted course, but activated a new surface state for a different part of its journey. The leading hypothesis is chilling in its implication. It was preparing for approach. A brighter surface reflects more radiation, reduces solar heating, and could signal the start of a new operational phase. Not survival, but engagement, possibly with something nearby. The inversion also disrupted spectrographic identification. The new skin made it harder to analyze composition, blocking many of the wavelengths traditionally used to determine material makeup, as if it wanted to be hidden. This single phenomenon, a comet that rearranged its skin like a machine, cracked open a dimension of inquiry that few were prepared for. Because if phase inversion was not the result of natural processes, it was either built or triggered, and either answer changes everything we think we know about interstellar visitors. At first they moved independently, erratic streams of plasma and particulate, each tracing a separate arc away from the nucleus. But late on the evening of January 3rd, something changed. The jets emerging from 3I Atlas began to cross. It started subtly. What had been parallel emissions began to shift, not in direction alone, but in timing. One jet fired, then paused. Another emerged moments later, but angled into the same vector. Then the reverse. The crossing wasn't violent, not yet. It was rhythmic, controlled, like a dance rehearsed in microgravity. Crossing jets are rare. In typical cometary behavior, jets burst from surface fractures when solar heat penetrates the nucleus and causes subsurface volatiles to erupt. They explode outward along the path of least resistance, but they don't aim, they don't wait, they don't switch roles, and they certainly don't cross like this. This new behavior wasn't lost on observers. Ground-based infrared arrays in the Canary Islands caught the first signs of the crossings, and then an orbital sequence from ESA's solar orbiter confirmed it. Two jets moving in mirror curves converging at specific distances, then breaking apart, only to repeat the motion minutes later. The geometry stunned analysts. These weren't just reactive bursts, they were phase-locked. They maintained rotational timing even as the core tumbled. The angle of emission and the distance to crossover remained consistent, like synchronized pistons in an invisible engine. It raised a possibility few were prepared to say aloud: intentional modulation. Some researchers postulated a gyroscopic mechanism at play. If the core housed a rapidly spinning substructure, perhaps with internal channels or vents, then centrifugal force could guide when and where outgassing occurred. But again, that would suggest some form of internal order, not randomness, not erosion, order. The crossing jets also began to create shadows, not cast by the comet, but within the coma itself. These darker voids twisted like interlocking fingers, patterns forming in the dust where light couldn't penetrate due to concentrated material. This effect, visible even in amateur scopes with decent contrast filters, gave the illusion of rotating blades, spirals, helices. One scientist on the Space Weather Net forum described it bluntly. It looks like something is using the jet crossings to steer. That comment, though speculative, was echoed in more official language during a closed-door meeting at NASA's Jet Propulsion Laboratory. The agenda was supposed to focus on orbital velocity drift after the Jupiter swing bee, but the data from the jet crossings overtook the conversation. If 3I Atlas had altered its course, and that had already been confirmed by multiple observatories, then the method was now under scrutiny, and these crossing jets, timed and aligned, became suspect. Avi Loeb, speaking later that night in a Harvard Symposium livestream, noted that the interplay between ejection events and resultant motion could indeed suggest a maneuver-like function, especially if the bursts are not uniform in mass or timing. He was careful to add that this didn't prove intelligence or design, but he didn't dismiss the possibility either. What made the phenomenon even more perplexing was its timing. Because hours after the first crossing sequence was logged, radio signals from 3I Atlas changed again. At 2117 UTC, the Very Large Array in New Mexico registered a new harmonic layer atop the prior Hertz frequency burst patterns. This new layer wasn't strong, barely above the noise floor, but it carried a signature beat, synchronized to the jet cycles observed optically. That is, the jet crossing pattern was now mirrored in the comet's emitted electromagnetic noise. That moved things into new territory, because if the object was coordinating physical motion with electromagnetic output, then it was, at minimum, aware of its own orientation. That level of awareness doesn't exist in natural celestial debris. Not in comets, not in asteroids, not in any object we've studied this deeply. The synchronization of energy forms, kinetic and radiative, suggested a feedback loop. And if that feedback loop was precise enough to maintain crossing jet timing over hours, it might persist. The next question became terrifyingly simple. What happens if these jets fire in new directions? If the crossing is a steering function, then 3I Atlas may not be drifting anymore. It may be piloting. Speculation ballooned. Some hypothesized that the object wasn't singular, but layered, a shell surrounding a secondary rotating body. Others leaned toward exotic propulsion theories, not because they believed in science fiction, but because standard thermodynamics couldn't account for what was being observed. And then came the silence. At 03:41 UTC on January 4th, all emission, both visual and electromagnetic, dropped to zero. No jets, no bursts, no light beyond standard solar reflection. 3R Atlas had gone quiet again, but the coma? It kept moving. The double helix in the dust trail continued to twist. The crossed voids persisted in shape, as if the object had handed control to its own wake. The silence didn't comfort anyone. It felt like a pause, a reset, a breath before another phase. By now, one thing was clear to every researcher watching. Whatever 3I Atlas was doing, it was no longer following the rules of passive flight. And if jet crossings were part of its propulsion, then it wasn't just moving, it was aiming. As scientists focused their attention on the thickening tail structure of 3I Atlas, something unexpected began to emerge, a series of shifting interference patterns, like invisible waves echoing through the material. At first glance, it seemed like the usual solar wind turbulence. But closer analysis from Hubble's high-contrast imaging revealed symmetrical fluctuations moving through the tail in precise intervals, almost like ripples in a finely tuned instrument. These weren't random, they weren't chaotic. They formed predictable waves with slight phase shifts occurring every few minutes. It was as though the tail was acting like a massive antenna or membrane, responding to something somewhere. Not emitting signals, but receiving. And that idea made several researchers pause. Because if this structure was reacting, not just emitting, then something out there was interacting with it. For context, comets often show irregularities in their tails. Solar flares, magnetic eddies, or directional turbulence can all leave their mark. But this wasn't that. The undulations didn't correlate with solar output. They weren't aligned with flare activity, and perhaps most curiously, they remained stable in direction even when 3I Atlas veered on its new trajectory. The patterns had a clarity to them, as if a hand had drawn them deliberately across the stream of particles. They would peak, then fade, and then peak again in a cycle. This repeatability made some at ESA and NASA wonder if they were looking at a naturally resonating object. A phenomenon we rarely observe on this scale. One hypothesis suggested that 3I Atlas may have entered a standing resonance with the magnetic field between Earth and Jupiter. If true, this could mean the object wasn't just passing through space but was caught, however briefly, in a kind of harmonic corridor. These corridors aren't visible to the eye, but they form where gravitational pulls and magnetic streams intersect across planets and the Sun. They're like invisible tunnels, and if 3I Atlas found one, it might be using it. This could also explain the elegant turn we had just witnessed. Rather than a chaotic deflection, the maneuver now looked more like a correction, a curve made along the walls of a pathway most observatories hadn't fully mapped. And that would mean its course wasn't just changing randomly, it was adapting. As the tail's interference waves continued to move in lockstep, an emerging fringe theory grew louder. What if this object was designed to remain in contact with some kind of external field? In this case, the oscillations wouldn't just be a side effect, they'd be essential, they'd keep it tuned, like a deep space compass. And it would raise an even larger implication that 3I Atlas may not have lost control, it might have just realigned itself. From Jodrell Bank in the UK to Cerro Tololo in Chile, radio astronomers began pointing their arrays toward the tail's central axis. If there was anything hiding in those harmonic fluctuations, even a whisper of a structured frequency, these teams would be the ones to find it. And within 36 hours, early data began to roll in. The first results weren't audible signals, they were ratios. Ratios between bursts, between intervals. Ratios that mirrored Fibonacci sequences and golden spirals. Numbers not random in nature, but often found in biological systems, galactic arms, and, intriguingly, ancient structures. It was too early to draw conclusions. But not too early to ask the question out loud. Was 3I Atlas interacting with something we hadn't seen yet? Or worse, was it reacting to us? The tail kept shimmering, silent, steady, and untouched by Earth's gravity. And deep inside that changing stream of particles a rhythm continued. Slow, deliberate, almost musical. And in the next hours, something else would change. The tail's length would begin to fracture, not break apart, but segment, and that's where we go next. As more observatories locked onto 3i Atlas in the wake of its tail's rhythmic oscillations, a subtle and unsettling development began to surface. The tail, once a long continuous filament stretching millions of kilometers behind the object, was starting to fracture, but not in the way you might expect from a natural event. These weren't chaotic breaks caused by solar winds or magnetic turbulence. These were segmentations, deliberate, clean, and evenly spaced. Each segment of the tail formed like a ribbon detaching from a central line. From low-orbit telescopes to deep space probes trailing the object, the data began to converge. The segments weren't just falling away, they were holding position, remaining suspended in space like floating markers, and with every new break the intervals between each segment remained constant. This created a pattern, one that looked more like an artificial sequence than a comet shedding mass. Some compared it to breadcrumbs, others to antenna nodes, but the overwhelming sense among scientists and analysts was one of strategy, not entropy. Something was being executed here, step by step. When the European Solar Orbiter passed across the periphery of the comet's tail, its magnetometers detected a sharp drop in background noise between the tail segments and a sharp spike within each one. It was as if each broken piece of the tail had become a self-contained node, each vibrating at its own frequency. When laid out across the data spectrum, these segments revealed an unmistakable harmonic scale, ascending from the base of the tail toward its end. This wasn't a comet in distress, it was a system playing a note. Immediately, speculation turned toward the idea of signal transmission. Was the tail acting as a transmitter or as a sequence of amplifiers? Could each segment be carrying part of a message, not in language, but in waveform, frequency, and distance? NASA convened a private emergency panel, pulling in astrophysicists, communication engineers, and mathematicians familiar with waveform encoding. The Pentagon sent observers, so did Japan, India, and the ESA. The fear wasn't that this was simply a comet breaking up. It was that 3i Atlas might be engaging in a behavior we couldn't classify, much less predict. Meanwhile, on Earth, the segmentation had become visible even to high-powered amateur astrophotographers. Night sky images began to circulate online showing clear bright knots in the tail, spaced evenly apart trailing back into the dark. The media didn't quite know how to handle it. Some outlets tried to downplay it as a normal dust fragmentation event. But deep inside private Slack channels, encrypted cloud logs, and internal research groups, the mood was shifting. Something about these segments mirrored a principle in quantum communication known as entangled relays. In that system, data is not moved linearly from point A to B. Instead, it's mirrored and distributed across nodes, allowing information to be preserved even if individual parts fail. If 3i Atlas was using such a system, these tail segments might be its version of secure backups. Or worse, they might be positioning themselves for coordinated interaction with something else, maybe even Earth. By the 12th hour after the segmentation began, AI anomaly trackers on Earth's magnetosphere flagged a strange reading. There were microfluctuations, far smaller than what a solar storm might cause, but consistent with the same rhythm as the tail's segmented pulses. The fluctuations weren't strong enough to affect technology, but they were synchronized. We were beginning to feel the echo of 3i Atlas's new formation, not just seeing it. And just as analysts started building predictive models for the rhythm, the entire pattern shifted, inverting, then reforming with a tighter interval, like a song changing key, or a system calibrating for new instructions. In the next phase, it wouldn't just be the tail changing. The comet's core, long dormant and shrouded in radiant ice, would begin to show cracks, and what was inside didn't match any known material on record. That's where we go next. When astronomers first observed the strange bend in 3i Atlas's trajectory, they expected it to eventually stabilize. Objects in space don't just make dramatic shifts without underlying forces returning them to balance. And yet, the Hubble footage told a different story, one of acceleration. Subtle at first, but undeniable. What began as a graceful curve away from its previous line of travel was now morphing into something else entirely. The velocity of the comet wasn't just increasing, it was increasing in a specific direction. Not random, not chaotic, but intentional, as if the comet was adjusting its own path mid-flight. Using deep space Doppler readings and combined optical frames, astronomers noticed that the forward momentum of 3I Atlas had changed vectors by a margin just enough to suggest a rerouting, but not enough to be explainable by solar radiation alone. Solar sails made of dust or gas might push a comet in certain ways, but here there was no evidence of outgassing strong enough to cause such a forceful turn. Instead, researchers began looking at the core. Had something activated within the comet to trigger this turn? The central axis, previously stable, was now showing micropulses in reflected light, as if heat or electromagnetic interference was emitting from its nucleus. Whatever was occurring at the heart of 3I Atlas wasn't visible, but it was exerting influence far beyond what natural physics should permit. This raised concerns not only in observational astronomy circles, but among those tasked with deep space object modelling for national defence. Was this object capable of manoeuvring? Had we been wrong to treat it as a passive body, like so many interstellar visitors before it? The rotation of the object had also begun to sync with the change in direction. Normally, when a comet rotates, the pattern is largely stable and dictated by internal ice distribution or mass anomalies, but in this case, the spin rate seemed to fluctuate rhythmically with the new course angle. Almost as though the comet were using its spin to maintain directional stability, like a gyroscope, but with more precision. As the velocity veer continued, mission control teams at ground stations in Hawaii and South America were tasked with running simulations. If this trajectory held, where would 3I Atlas be in 72 hours, then in 48? And finally, what if it veered again? To everyone's unease, each new data packet refined the path closer and closer to orbital intersections with magnetic fields, regions of space known for their ability to disturb, trap, or redirect high-energy particles. This made no sense unless the object was reacting to them. One particularly revealing frame taken just before the veer became most dramatic showed a faint trail, a streamer of ionized particles curling outward like a tail and then sharply retracting inward. Almost like it had overreached, sensed something, and pulled back. That moment might have been the signal that the object wasn't drifting. It was responding. No comet should be able to do that. The broader scientific community remained cautious. Some called it coincidence. Some pointed to hidden gas pockets that might have ruptured. But others weren't so sure anymore. When nature bends, it does so in patterns we can predict. But this felt like a reply. A change made with awareness. As the veer continued, so did the tension. Space wasn't empty anymore, it was reactive, and for the first time, it felt like 3I Atlas was no longer the visitor. It was the pilot. As 3 Atlas continued along its new veering trajectory, eyes turned to one particularly concerning alignment: Earth's outer magnetosphere. Not because the comet was heading for direct impact, but because it wasn't. Instead, its projected path now ran nearly parallel with the most sensitive regions of Earth's electromagnetic environment, and that presented a new kind of problem, one that had never been modelled. What concerned the European Space Agency the most wasn't the comet's speed or brightness. It was the strange synchronicity forming between its spin, its adjusted course, and the invisible shape of our planet's magnetic field. Like it was tracing the outline of a structure, a boundary, as if this interstellar body could see magnetic fields and was using them. The idea seemed absurd until the data refused to go away. The magnetosphere isn't a uniform shell. It has gates, windows, temporary tears and oscillations triggered by solar wind, CME pressure, and planetary motion. Most of the time these open and close without consequence, but occasionally highly charged plasma particles pour through those weak points. Now, for the first time in recorded history, something big was intentionally gliding through the corridor like it had a map. At NASA's Goddard Space Flight Center, spectromagnetic overlays of 3I Atlas showed something strange. A series of pulsed emissions, not optical, not radio, but resonant, timed out evenly. Each one matched fluctuations in Earth's outer magnetic field, as though the comet was pinging the structure, sensing the shape of the magnetic shield and adjusting accordingly. Scientists tried to find historical parallels. Solar flares? No match. Magnetar flares? Too intense. Cometary ion tails? Not directional enough. The pulses from 3i Atlas were subtle, but clean, and they were received in a way that made no sense. Earth's own magnetic anomalies began to vibrate in harmony. This wasn't just an object passing through, it was sounding the gate. One theory, put forward quietly in internal memos, suggested that this might be a test, not a weaponized action, not an assault, but a calibration, like sending a submarine ping to detect seafloor depth. Only now, the sea was Earth's protective field, and the ping, it was coming from a comet that had no business knowing how to do this. At the edge of this so-called magnetic gate, auroras began flaring unexpectedly. But not at the poles. Instead, thin vertical ribbons of green and purple light flickered near the equator, something no one had seen before. Atmospheric scientists rushed to dismiss it as an unusual solar byproduct. But deep inside geomagnetic modelling labs, something colder set in. The gate wasn't just being used, it was being activated. There was growing concern that this wasn't about Earth. It was about what came after Earth. The gate may have been one of several magnetic tunnels laced across our solar system, interlinked by gravity wells, solar wakes, and planetary resonances, the kind of structure you'd never notice unless you were mapping fields, not surfaces. And now, humanity had a visitor that wasn't stopping to look at the planets. It was gliding through their invisible architecture like it had been here before. If 3 Atlas was following magnetic topology instead of gravitational inertia, everything changed. Trajectories, intent, timelines. It meant the comet was using the very skin of our solar system to move, like a ship sliding along rails we hadn't yet discovered. The magnetic gate wasn't just a field, it was a highway, and 3i Atlas had just merged into traffic. As 3i Atlas crossed deeper into the zone adjacent to Earth's magnetic gate, another unexpected event unfolded, one that had nothing to do with light signals or magnetism. It was temperature, or rather, the absence of it. Satellite arrays operated by the Japanese Aerospace Exploration Agency, JAXA, picked up a strange pattern trailing directly behind the object, not a standard thermal wake, like the kind left behind by a spacecraft or meteor streaking through upper atmospheres. This was different. In fact, it wasn't warmer than the background, it was colder, significantly colder. 3i Atlas was leaving behind a corridor of sub-zero vacuum, a sharp drop in ambient cosmic temperature that seemed to resist reabsorption. It was as if the comet had pulled something out of the surrounding space as it passed. Instruments aboard ESA's solar orbiter confirmed it, a consistent linear dip in thermal activity trailing directly behind the object for thousands of kilometers. This stunned scientists. Nothing in known physics supported this kind of effect at such a distance. Even black holes, the ultimate thermal sinks, didn't behave this way at these scales. Whatever this was, it wasn't simply an energy deficit, it was an imprint, a negative echo, a thermal scar on the canvas of interplanetary space, and it didn't stop. The path 3i Atlas followed continued to stretch this cold filament behind it, straight through solar wind channels. It deflected particles, altered flows, and most alarmingly, it persisted. Hours after the object had moved beyond a region, the thermal drop remained. Days later, in some cases, it acted like a reverse contrail, only colder than cosmic background radiation, and more stable than expected in an environment full of solar turbulence. NASA scientists dubbed it the thermal wake phenomenon. Theorists scrambled for explanations. Was the object harvesting thermal energy? Was it interacting with dark matter particles? Some hypothesized that this wake wasn't just a side effect, it was the method by which the object navigated. Like an animal using echolocation, but instead of sound, it used thermal voids. It might have been creating cool corridors to glide through more efficiently. Others speculated something more radical. The object might be interacting with space-time in a way that siphoned latent heat from the medium itself, not by absorbing it, but by shifting it out of phase. If true, it wasn't a passive body at all. It was actively reshaping the environment around it for travel. Then came the warning. The JWST infrared sensors, which had long been watching 3i Atlas from deep space, revealed a curve in the wake, something akin to turbulence. But unlike atmospheric turbulence, this thermal turbulence sent shock waves into the surrounding solar plasma. It created oscillations that raced toward Earth and Mars simultaneously. ESA ground stations caught them first, followed by a flurry of alerts at NOAA. It wasn't dangerous yet, but it was replicable. Like a stone thrown into a still lake, the comet's movement had created a ripple in the invisible thermodynamic structure of our local space, and that ripple now stretched hundreds of thousands of kilometers in width. It pulsed once every 97 minutes, the same interval that 3I Atlas emitted its earlier resonance pulses. It wasn't a coincidence. This wasn't just a comet passing by. It was drawing something behind it. Whether it was a natural reaction or an engineered system was unknown. But the thermal wake it left was now being studied as more than a side effect. Some began calling it a dragline. Others whispered something colder, a tether. As global space agencies focused on the comet's baffling thermal wake, a deeper concern was quietly growing among those studying the data. The wake wasn't dispersing. In fact, it was condensing. And that led to one question nobody wanted to answer aloud. Was Thros Atlas still connected to something else? Theories started to converge around an unsettling idea. What if the object wasn't acting independently? What if the wake wasn't just a trail, but a tether? Not metaphorically, literally. Researchers at the Indian Space Research Organisation, ISRO, running parallel spectrometric scans, noticed something buried inside the colder corridor. A pattern. Rhythmic micropulses of gravitational distortion occurring every 5.6 seconds, just barely strong enough to shift surrounding solar wind vectors. They weren't random. They repeated with machine-like precision. Normally, such fluctuations could be dismissed as data noise, but this was different. They were locked to the motion of the wake, not the comet itself. These pulses weren't being generated by 3I Atlas. They were being relayed through the wake, like messages carried along a cable. NASA's Jet Propulsion Lab corroborated this, showing that the oscillations travelled faster than the comet's own movement. Something was transmitting signals or momentum up the line, not down. That broke every model they had. Scientists gave it a name, the tether theory. According to this model, 3I Atlas wasn't a self-contained object drifting through the solar system. It was a node, a terminal point on a vast invisible conduit stretching backward through the path it travelled, possibly out into deep space. A system, a connection, what lay at the other end. That was the horrifying part. If the tether was real, if this was some form of guided transit mechanism, then the object might not have arrived in our system. It might still be arriving. Or worse, it could be one of many. An antenna from a distant origin, a seeding vessel tethered to a hidden station, or part of a galactic relay that only now made itself visible because Earth had fallen into range. Even Avi Loeb, who had until this point maintained cautious optimism, publicly voiced his concern. If the tether model holds, we are not looking at a single object anymore. We are looking at a system, one that may extend far beyond our instrument's reach. On December 30th, a breakthrough. ESA's solar orbiter caught a rare side profile of the wake's core using ultraviolet scattering techniques. Inside the deepest thread of the thermal void, a faint shimmer appeared, not light, not energy, a shadow, a flicker of something stretching behind 3I Atlas, almost like a strand taut and vibrating. It wasn't material, but it wasn't nothing either. And then it twitched, just once, as if something at the far end pulled it. All around the world, mission directors and astrophysicists froze. If that was real, and not a glitch, then the implications were staggering. 3 Atlas hadn't just passed Earth. It might still be anchored. A quiet signal was sent out from NASA. Increase Lagrange point monitoring. Expand magnetotail tracking. Check the backside of every major planet's shadow. If the tether connects to something else, we need to know what. And we need to know before it gets pulled tight, because tethers only exist for one reason, to bring something through. The first clue didn't come from a space agency. It came from a deep-sea neutrino observatory. In the ice-laden darkness below Antarctica, a sensor cluster at the IceCube Neutrino Observatory picked up a peculiar cascade, not of particles from the sun, but something far stranger. Neutrino echoes. Normally, neutrino bursts are associated with cosmic events like supernovae or gamma-ray bursts. They arrive in bursts, directional and erratic, often traced back to violent phenomena thousands of light-years away. But this was different. The echoes came in intervals, Not random, not explosive. They pulsed, low, uniform and measured. And the strangest part, they weren't coming toward Earth, they were moving past it, through it, like ripples on a taut rope. By the time scientists at IceCube linked the pattern to the tether theory surrounding 3I Atlas, it was already being echoed in other systems. Seismographs in Norway began recording deep Earth tremors with no tectonic source. Magnetometers in Brazil showed bizarre sub-ionospheric resonance that didn't match any known geophysical input. At first, these seemed unrelated, but when layered together, when the neutrino signals were plotted against the tremors and magnetic undulations, a picture began to emerge. It looked like a wave, a slow, methodical pulse travelling down an invisible conduit that passed through Earth itself, like a message or a tug. NASA confirmed it that same evening with a whisper-quiet press memo. "We have credible indicators that 3I Atlas is experiencing reverse momentum." That meant only one thing. Something was pulling back. In space, the object's trajectory, once assumed to be on an outbound curve toward Jupiter, began to slow, subtly at first, but unmistakably. Its acceleration vector was not consistent with solar slingshot behavior. It wasn't just curving, it was resisting forward drift, like a kite reeling back to its origin. Avi Loeb issued an urgent joint paper with astrophysicists from the Kavli Institute. In it, he postulated 3 theoretical causes for the reversal: a remote mass anchor, something massive, invisible, and gravitationally dominant far beyond Jupiter, exerting a controlled draw. A propulsion counterpull, not from the comet itself, but from a return mechanism embedded in its trail. A dimensional tether, a theoretical concept where an object is linked to another domain via non-local connection, meaning it might be getting pulled from outside our universe. The public never saw that third theory. But in internal memos across NASA, ESA and Roscosmos, the term interdimensional reversal event was used. Quietly, carefully, often with a question mark. Meanwhile, Hubble's long exposure imaging of the tail revealed that the supposed anti-tail had begun to restructure. Instead of flowing outward, its filaments bent inward, forming a vortex shape. It looked less like a tail and more like a noose tightening around the object. And through it all, 3I Atlas remained silent. No outbursts, no flares, no new jets, just motionless obedience. As if responding to something we couldn't see. On January 2nd, Solar Orbiter recorded the final twist, a sudden 1-degree yaw rotation in the object's orientation. Nothing natural caused it. No solar wind shift, no magnetic interference. It just turned toward Earth and paused. That was the moment when Mission Control in Pasadena stopped treating 3I Atlas as a comet. From that point forward, they labelled it what it had always acted like, a vehicle, one that had just received instructions, and now something was pulling it home, or closer. And Earth, for reasons no one could explain, was still in the way. As scientists examined the Hubble data from January 4th, one anomaly stood out, so subtle, yet so impossible to ignore. A colour shift. Not in the way stars redden as they move away, or the familiar blue shift of objects approaching at speed. This was something stranger, something that sat in between, but wasn't quite either. The colours coming off 3I Atlas's tail began showing an oscillation, a rhythmic shimmer between hues that didn't align with standard comet emission. Normally, when dust and gas trail a comet, we can predict the light they reflect and emit. But this time, the wavelengths registered by the Hubble team didn't match any known model. First came the pale green, which isn't unusual on its own, caused often by diatomic carbon. But that hue would subtly flicker. One frame would show a faint purple overlay, the next, a flash of yellow-orange around the edges. Not enough to be dramatic to the naked eye, but under spectral analysis, the transitions were irrefutable. At first, the team thought it might be an artifact of solar reflection interacting with magnetic fields, but when they compared the same zone across 3 other observation points, each recorded the exact same pattern. It wasn't a lens effect, it wasn't solar noise. The colours were genuinely changing. So what was causing it? The leading theory suggests that 3I Atlas is emitting material in pulses rather than a constant outgassing. And these pulses are composed of different compounds. The comet isn't just shedding ice and dust, It's shedding different substances in distinct waves, almost as if it's turning on and off certain jets with specific chemical makeups. This would explain the rhythmic shifts. Imagine a rotating nozzle, releasing bursts of vaporized sodium, followed by cyanide molecules, followed by iron particles, each with their own light signature when hit by sunlight. If this cycle repeats in seconds or minutes, the tail would shimmer like a code, like a beacon transmitting a colour-based sequence across space. Naturally, that idea unsettled many, because comets do not pulse their emissions in patterns. They erupt, they vent, but they don't sequence, and they certainly don't emit changes on such short timescales that they appear like an organised rhythm. Some called it a coincidence of chemical layering, others weren't so sure. The deeper implication was haunting. What if the tail's colour pattern wasn't just chemistry? What if it was information? There have long been fringe theories that light can carry more than energy, encoded data, intentional signatures, or even biological signals embedded in frequency. While those claims remain on the edge of accepted science, Hubble's colour shift stirred the question again. Because it wasn't just the comet's behaviour, it was how consistent it was, how it repeated, how the spectrum danced not like a chaotic eruption, but like a waveform. The final images from this Hubble batch ended on a frame that stuck with the team. The comet's tail bloomed into a tricolour bloom, green, violet, then briefly, white. A near-perfect white band, something almost never observed in natural solar reflections. It lasted a single frame, but it was there. The white band, unlike the others, carried a full spectrum signature. It wasn't filtered by a single compound. It was a mixture, a convergence, as if the comet, for a brief second, aligned every colour into harmony and then blinked back to its chaotic state. Scientists logged it as a flare, a burst, but some saw something else in that frame, a signature of completion, a punctuation mark on an otherwise unresolved pattern, as though the comet had said something, and that white flash was the period at the end of its sentence. The tail hasn't repeated that full spectrum bloom since, but the memory of it now colours everything that follows. Because once you've seen a light speak, it's hard not to listen again. The photographs from Hubble had already revealed more than anyone expected. Colour shifts, pulses of unfamiliar compounds, and a white spectrum flare that defied standard comet behaviour. But one analyst wasn't satisfied. Dr. Elena Rousseau, a veteran image processor at the European Southern Observatory, had spent her career uncovering hidden structures within astronomical noise. And as she stared at the tail of 3I Atlas, she felt something was wrong. It wasn't the colour anymore, it was the geometry. She zoomed in on a deep exposure composite, layering time-stacked images from Hubble's sensors over a span of 7 hours. Most comet tails blur with motion in these stacks, smearing outward as solar wind and momentum stretch them into long curves. But this time, Rousseau noticed a strange consistency. Amid the blurring gases, one region remained fixed. It was subtle. A linear thread no wider than a star's diffraction spike running dead centre through the tail's middle zone. No curvature, no feathering, just a sharp, knife-straight line. And it wasn't an artifact. When she pulled raw data from multiple angles and exposures, the same line appeared every time. That shouldn't be possible. Rousseau ran edge detection filters on the central tail and amplified the contrast. What emerged was a haunting outline. Faint, but unmistakably deliberate. A hexagon. Not a perfect one. This wasn't some glowing sci-fi portal, but 6 equidistant nodal points forming a repeating shape down the tail's spine. Each point glowed just a fraction hotter than the surrounding gases, invisible to the naked eye but clearly active in ultraviolet. Even stranger, the intervals between the nodes were consistent, like vertebrae, or antennae, or, if one dared to say it, designed. Rousseau didn't want to speculate, but the longer she stared at it, the more the pattern stared back. She forwarded the image to colleagues in Austria and Japan who confirmed it. The tail of 3I Atlas wasn't random. Embedded in its brightest emissions was a repeating structure, symmetrical yet embedded in turbulence. Some tried to model it as a rotating crystalline formation, perhaps ice refracting light into stable shapes, but the UV brightness disproved that. This wasn't reflective, it was emissive. Something was generating those nodal points. Then came a breakthrough from a lab in Kyoto. A team cross-referenced the hexagonal intervals with data from plasma frequency emissions, specifically the comet's ion tail behavior, and noticed the emissions pulsed every time a hex node brightened. In other words, every time the hex pattern lit up, the comet released a spike of ionized gas, like a breath, a beat, a rhythm. Now the color shifts made more sense. The emissions weren't random, they were structured outputs. The hex nodes weren't shapes, they were emitters. This raised a terrifying question. Emitters of what? It was too early to say definitively, but early simulations showed the tail was behaving like a massive phased array, a system capable of sending directed energy or information using coordinated light emissions. That technology exists on Earth, in a crude form used in experimental lasers and radio transmitters, but 3i Atlas was doing it, with its tail, from millions of miles away. With precision beyond anything humanity could engineer at that scale. That meant two things. First, this was not just a comet. It was, in function, an active platform, a system emitting coordinated energy through spatial symmetry and timing. Second, and this was the part that scientists were whispering about behind closed doors, this platform might be capable of communication, not passive signals, not accidental flares, but active, structured transmissions directed towards something or someone. The comet was broadcasting, and the pattern, repeating, symmetrical, timed, suggested a purpose. Was it trying to send a message? Or worse, was it waiting for a response? In silence, the world's top observatories turned their instruments back toward 3i Atlas, no longer studying a rock in space, but something far more deliberate. The shape in the tail wasn't just geometry, it was intent. As the Hubble team traced the altered path of 3i Atlas, another subtle yet telling anomaly surfaced, not in the comet's structure, but in what it left behind. A new series of measurements focused on the dust trail, the streak of debris particles that typically fans out behind any fast-moving interstellar object. But this trail was unlike anything seen before. It didn't simply follow the usual elliptical arc that results from solar wind, radiation pressure, and momentum loss. Instead, it appeared to bend, subtly, and then increasingly, away from the primary arc. This strange curvature in the dust trail wasn't immediately obvious to the human eye. In fact, it was discovered through motion mapping algorithms that compared several layered Hubble frames over time. When the digital overlays were applied, analysts saw it. A faint divergence, almost like a second ghost trail, forming on the opposite side of the initial debris arc. That divergence wasn't just aesthetic, it was mathematical. The angles were too precise, too consistent to be random turbulence in the solar wind.